Let me welcome you to this MOOC course on VLSI physical design. In the first module that we shall be starting now, we shall be discussing some of the basic concepts on VLSI physical design automation. So, in this first lecture, we shall be looking at some of the introductory topics. I would first like to talk about the rough coverage of this course. So, as you can see, in the first module we shall be talking about some of the introductory concepts. So, we shall try to motivate you regarding the need and the importance of physical design automation in the VLSI design cycle. Then in the successive modules we shall be looking at some of the very important components or steps in this physical design automation step. For instance, in the second module we shall be talking about floor planning and placement, and as we shall see, partitioning of a design is also equally important at this step. Module 3 would discuss the various aspects of routing. So, here we shall see that there are many different kinds and types of routing algorithms and routing problems involved in the design cycle. Then in the next two modules, we shall be looking at a very important topic of modern day VLSI design, namely static timing analysis. So, here we shall be talking about the various timing issues and the different ways in which you can enhance the performance of a design or a circuit. Module 6 will talk about the signal integrity and crosstalk, which are related. Then we shall be discussing the various clocking issues, and in particular how the clock nets are routed, which are sometimes typically called clock tree. Then in the next two modules we shall be talking about the very important issue of reduction of power in circuits. Then in the last two modules we shall be considering noise analysis, layout compaction, then physical verification with final sign off before the chip is designed. So, essentially what we are talking about in this course is that starting from the behavioral specification we can arrive at the circuit netlist in some form, and from the netlist what are the different steps that we need to follow in order to finally arrive at the physical layout at the lowest level. So, during this course we shall basically be talking about the various aspects and the tools and technologies that are used in the process. Okay. Now, talking about the main focus of the course, well, as you can see, we would be talking about digital design and we would be talking about physical design automation. So, digital design means, as you know, that we are only considering circuits and subsystems which work on digital signals in this, you can say, topic digital design. But as you know, in a modern day system or a chip, let us take our mobile phone for example. So, in this mobile phone we have some VLSI chip which contains not only the digital subsystems or circuit components, but also other analog and communication circuitry embedded in a single silicon package. So, we call them mixed signal digital and analog combined kind of ICs. So, whatever discussions and concepts we would be talking about, they would apply not only to digital circuits, but also to this kind of mixed signal and analog circuits as well. Okay. And physical design automation, as I had mentioned, it basically consists of the different intermediate steps that need to be followed to translate a given circuit netlist into the final layout which can be given for final fabrication of the chip. Okay. This is the scope of physical design automation, and this is the scope of the discussions that we are expected to cover as part of this course. So, let us briefly talk about the digital design process. So, as you all must be knowing that the complexity of circuits have been increasing very rapidly over the years, primarily because of improvements in semiconductor and fabrication technologies. Okay. So, in the beginning, in the 70s and 80s, we used to talk about 5 micron technology and things like that, but today we are into deep submicron technology. So, here very recently devices with 14 nanometer feature sizes have already come to the market. So, we are seeing a fantastic growth in the semiconductor technology and the way we are able to pack more and more devices in a single circuit or a chip. Okay. So, in the digital design process, we are not only looking at the increased sizes of the circuits, but also the associated complexity involved. What does this mean? You see, handling a circuit with 100 gates and handling a circuit with 1 million or 1 billion gates is of course not the same. We need much more effort, much more sophisticated tools and technologies and techniques to handle this circuits of extremely large sizes. Say earlier when the circuits were small, some of the steps we could have done manually, but in today's world manual design and manual you can say analysis is almost ruled out. The circuits are too large to be even you can say means it is very difficult to even think about doing these steps in a manual fashion, because it will take years to do even a very simple small part of it. Okay. So, as I said, the fabrication technologies have improved and the computer aided design or automation tools have become extremely essential in the present day context because of the increasing size and complexity of the circuits. But the issue is that if you look into the available CAD tools that are there in the market, you will find that there are many such available tools. So, one question that naturally would come into mind, which tool should I choose for my design? So, of course, the kind of tool that you will be choosing in your design may depend on a number of factors. Cost can be one of the most important issues. Some of the tools, though may not be the best possible among the alternatives, but the cost may be affordable for you to go for that. Some people, they also do some kind of a mix and match. Like let me give you an example. There is a research group in our college who actually carry out the VLSI digital design process, design flow it is called, as a combination of two parts. The higher level part, that is called the front end design, that is carried out using the CAD tools available from Synopsys, which is quite well known, and the later part which is called the back end design or the physical design, that is carried out using the Cadence CAD tools. So, as you can see, depending on the convenience and the way you are able to use the tools, you can have a mix and match. So, you can take the best of both worlds, for example, in this case, right. So, the present trend, as I had mentioned, is to standardize the design flow. Design flow means what are the tools I would be using. Like I had said, in our case we would be using Synopsys in the first few steps and Cadence in the later steps. And of course, with the with the increasing emphasis on battery operated devices and various mobile computing platforms. So, the greater and greater emphasis have been laid on low power design without sacrificing performance. Okay? Fine. So, let us look at these two pictures. So, you will get a very rough idea. So, the picture on the left shows one of the first ICs that were manufactured in the year 1961. So, this IC comprised of only a few transistors, but in contrast to look at this photograph on the right side, this corresponds to the Intel Nehalem quad core processor, which houses more than 1 billion transistors. So, you can see the sea of change that has taken place, okay, over the years. And here we have another very important you can say empirical rule or law that has driven us over decades. Gordon Moore in the 1970s, even earlier than that, he predicted the way the circuit, you can say the circuit design and fabrication technology would evolve over the years. So, what he predicted was that the number of transistors or the basic components that you can pack inside a single integrated circuit would be doubling every 18 months or so. So, this means some kind of an exponential growth over the years. So, initially people thought that well, it is fine, at least for a few years we would be able to sustain this exponential growth, but finally this has to taper off, we cannot continue this for long. But surprisingly, with the developments not only in semiconductor technology, but also with enhancements and improvements in the architecture of the systems, the way we are building the chips, multi-core architectures that we see today. So, we have been able to sustain this exponential growth over the years till today. So, this slide, if you see, so on the y axis you see the number of transistors in an exponential scale, and on the x axis you see the years starting from 1970 up to 2015, it is shown here. So, you can see in this graph that here from the first microprocessor that came to the market, it is here 4004, up to the latest Sandy Bridge and Ivy microprocessor multi-core systems which Intel is coming up with. So, Moore's law predict that this curve will be a straight line. So, as you can see, this straight line behavior is still being maintained, right. So, because of this exponential increase in growth, one thing you can easily see that design complexity is also increasing exponentially, which means automated computer aided design tools are essential. It is not an optional means this is not an optional thing anymore. So, you do not have any choice, you will have to use such tools, and of course, you will have to follow some well defined design flow in order to control and manage the complexity of the designs. Okay. Okay. Now, I had said that over the years the circuit complexity in terms of the feature sizes have reduced in sizes. So, I will show a slide quickly, very you can see the pictures. So, on the left I have shown a classical CMOS transistor consists of an NMOS, CMOS gate in fact consists of an NMOS transistor and a PMOS transistor. So, they are laid out on the same silicon substrate. So, with this classical CMOS kind of design, we have here we have been able to sustain the growth up to as small as 22 nanometer technology. But today we have newer ways of fabricating this MOS transistor. So, one of the most popular ways is called FinFET, where the transistors look like fins, not they are not laid out in a flat fashion, but they are laid out as fins which require much smaller area to fabricate. So, FinFET can go down to much smaller feature sizes, and as you can see, FinFET has designs has been reported which has gone down up to 14 nanometer, and very recently some communication chips from Qualcomm have been reported. They have used FinFET 14 nanometer technology. Looking into the future, we really do not know, can quantum computing be an option for us? So, this only time can tell, but of course, many researchers are working in this direction. So, let us hope that we will see something very interesting in the near future. Okay, let us now talk about the design flow. Now, as I said, design flow is essentially some standardized design procedure where you will be using some set of defined steps that are to be followed in order to translate a given design into the final fabricated chip that you are targeting for. Now, there are many steps in this design flow. It is not just a single step which is automated. There are a large number of intermediate steps, some of which are mentioned here. You typically start with the specification of a system, what your system is supposed to do. In the next step, you go for synthesis. Synthesis means you are trying to translate your this specification into some kind of circuit netlist. Now, again the synthesis may not be in a single step, there can be a multiple levels of synthesis, as we will see little later. Then in order to verify whether the synthesis process is correct, we usually use simulation to verify that whether the circuit netlist that we have obtained behaves in the same way as per the original specification. Then finally, we go down to the layout, which is now quite ready for fabrication, but of course, in the process we also carry out testability analysis, because whatever we design, there can be manufacturing defects, and after fabrication each and every device has to be subjected to elaborate testing before it can go to the market. Okay. So, and there are many other steps. This is a very simplified design flow, a few of the steps that are shown. And as I said that we must use computer aided design tools, and let us see how these tools typically work. Now, one thing, the inputs and the outputs of these tools are now fairly standardized, so that you can say interoperate multiple number of tools, because they work on the same input and output formats. So, we typically give our specification in terms of a description language, which you call as hardware description language or HDL. Okay. So, these computer aided design tools are based on hardware description languages. These HDLs provide ways to represent both the inputs as well as the outputs of the various steps in the design flow. So, essentially a CAD tool will transform its input, which is in HDL format, into an output which is also in HDL format, which will contain more detailed hardware information. Like some examples are here, you can translate from a behavioral level specification to register level specification. So, what is register level specification? Register level specification means a kind of circuit netlist which consists of components or modules like say buses, registers, adders, multipliers, multiplexers, some bigger functional modules or blocks. This is called register transfer level specification. Now, again in the next step you can translate this RTL or register transfer level specification to gate level specification, where you translate everything into basic logic gates and flip flops. And in the last step, this gate level specification might get translated to the final transistor level specification, which is sometimes called physical design. Okay. Now, talking of the hardware description languages, usually most of the people use one of two languages, Verilog and VHDL. Of course, the choice is up to the designer or the person uses it. Both of these languages are equally capable. They can be used to model any designs, any circuit, and also can be used in the synthesis flow, in the design flow along with the CAD tools. So, as I said, designs are created typically using these languages, which can be transformed from some higher level of abstraction to a lower level of abstraction as time progresses. Okay. So, this diagram gives you a simplistic view of design flow. Simplistic means I am not showing all the steps involved. So, what I am showing? I am showing some steps which, starting from a design idea, you first carry out behavioral design, where you model your idea in terms of flow graphs and pseudocodes. I shall give some examples. Then you go for data path design, where you translate your design into a register transfer level architecture, bus, registers, adders, etc. Then you go for logic design, where you translate them into gates or flip flops. Then you go into something called physical design, where you translate these into the final transistor level layout, which is now ready for fabrication or manufacturing. So, once you have fabricated, you can finally get your chips, using which you can create your circuit boards. Now, let us briefly look at some of these steps to just understand how this works. Let us say behavioral design, what does it do? Okay, let me just try to take an example. Suppose I have some operation to do, say, so I am multiplying two numbers B and C and I add it to D. So, this is one way of specifying what I want to do, but when I talk about behavioral level representation, so this same specification I can translate it into a flow graph, which might look like this. This multiplication is carried out with B and C as the inputs, and there will be another addition step where this will come and also D will come, and finally you get A. This is one example. Suppose I can have an example like this: if some condition is true, then you carry out some step or a set of steps S1, else carry out S2. So, again this can be translated into some kind of a data flow graph, which can be modeled like this. So, you check the condition A, if this is true, then you go for S1, if this is false, you go for S2. So, what I essentially want to say here is that given any high level description in Verilog or VHDL, the first step would be to translate those language constructs into data flow graphs, which can be translated into, you can say, data paths and control paths for the next levels of design. Now, in this diagram you see that your next step is your data path design, where you come to the bus or the register level structures. Let us see how these register level structures look like. Like here I am giving an example again. Suppose I have a register R1 which holds some data. So, at this level we are not talking about the variables, but we are talking about the hardware registers. Then we talk about a multiplier. This is a multiplier circuit. So, it can take the inputs from R1 and R2. The output of this multiplier can go to another register, say R3. Then we can have an adder. So, one input of this can come from R3 and the other one can come from another register R4. And suppose the output of this adder I want to store back in register R2, then I will have a connection like this. So, this is one way in which you can implement that operation, as I had mentioned, B into C plus D, where B would be stored here, initially C would be stored here, they would get multiplied, then added with D, and the result will be stored in A, which again would be stored here. I will also store A in this register. Okay. So, this is an example of a register level design. Okay. In the next step, we come to the gate level design. Gate level design you already know, where you can have gates or flip flops. Okay, let me take one very simple example of a gate level design. Let us say I have some gates, then I can also have some flip flops. Let us say I have a D flip flop with the output Q. The output can come here, let us say. So, there will be a clock input to clock this flip flop. So, gate level design will look more like this. So, each of the register level components like your registers, multiplexers, then adders, they will get translated into a gate level design like this. And finally, from this gate level design, each of these gates and flip flops can be translated into equivalent transistor representation. For example, this NAND can get translated into this equivalent CMOS gate. These are two N type transistors, let us say A and B are the inputs. These will be P type, this is also A, this is also B, and this is the output. This is the CMOS representation of a NAND gate, 2 input NAND gate, right. And at the end, when you translate this into layout, then you can have something like this. You can have metal layers, 2 metal layers, then you can have some diffusion layers, then you can have some polysilicon layers like this. And the output you can possibly take from here through some connection or contact. So, this is a very rough sketch of a CMOS NOT gate. Now, here we see that the final layout consists of nothing but various rectangular shapes, and some of the rectangular shapes can be on metal, can be on diffusion layer, can be on polysilicon layer, and also there are some contact connections. Here there is a contact, here there is a contact, here there is a contact, and so on. So, in the final layout, it is nothing but a sequence or a set of large number of rectangular shapes. Okay. This is the, you can say, in this step, when you talk about transistor layout, it is nothing but those rectangular shapes at the end. So, the steps in the design flow I have already mentioned them. behavioral design, data path design, logic design, physical design, and finally, once you have those rectangular shapes, you can create the masks and you can go for fabrication of the chip. Okay. So, now in addition to this, you have a few other steps also which you often carry out. For example, to check whether some step or translation is correct, you typically carry out simulation. Simulation can be carried out at various levels like logic level, switch level or circuit level. Formal verification is also a very important tool to verify the correctness of designs, and of course, testability analysis and test pattern generation are also very important, because you need to test the manufactured devices. So, with this we come to the end of this first lecture. Thank you.